Can you see this screen?
Yes.
Yes. So good morning, everyone. Let me first thank Professor Nathanson for giving me an opportunity to speak here. I'll be speaking on weighted zero-sum constants and inverse results. So this is the outline of the talk. First, we'll be seeing introduction. Next, we'll determine weighted zero-sum constants. First for cyclic groups, then for other finite abelian groups. And lastly, we will look at some inverse problems. So first, some definitions. Let G be a finite additive abelian group. Let its exponent be n, and let A be a non-empty subset of the set 1 to up to n minus 1. By a sequence over G, we mean a multiset of elements of G, and we will be writing sequences in multiplicative notation as we have written here. So a sequence x1, x2, xl over G will be called an A-weighted zero-sum sequence if there exist elements A1, A2, AL from set A such that A1, x1 plus A2, x2 plus AL, xl is 0, where 0 is the identity of the group. Here we call this A as a weight set. It will always be non-empty, of course, and even though we do not mention it, it will always be taken to be a subset of this set 1 to up to exponent of G minus 1. The next definition, the smallest positive integer m such that any sequence of length m has a non-empty A-weighted zero-sum sequence is called weighted Davenport constant of G, and it is denoted by dA of G. Let k be a positive integer. The smallest positive integer t such that any sequence of length t has an A-weighted zero-sum subsequence of length kn is called the generalized Erdos-Ginsburg constant, or shortly generalized EGZ constant with weight A, and we denote it by skna of G. So when k is 1, this generalized weighted EGZ constant is denoted by SA of G, and we simply call it EGZ constant of G with weight A. When Kn is the order of the group, it is denoted by EA of G, and we call it weighted Gao constant of G with weight A. In particular, if the weight set is the singleton one, then these constants dA of G, EA of G, and SA of G will be respectively the classical Davenport, Gao, and EGZ constants. In 2012, Grenkiewicz, Marcha, and Audas proved that for a finite abelian group G of order n and weight set A, EAG is equal to DAG plus n minus 1. Now, because of this relation, it is sufficient to determine DAG. We will get the value of EAG immediately. So in this talk also, we will be determining DAG and SAG. So this we will get by this relation. And in case of cyclic groups, SAZN will be equal to EAZN. So it is sufficient to determine DAZN only. In 2006, while introducing this weighted generalization of zero-sum constants, Adhikari, Shen, Friedlander, Konyakin, and Topaladi took this weight set plus minus 1, and they proved that with this weight set, EAZN is equal to flow log to n plus n. And by this we get DAZN is equal to flow log to n plus 1. We extended this weight set to this set plus minus 1, plus minus 2 to plus minus k, where k is an integer between 1 and n by 2. And with this weight set, we could prove that DAZN is equal to flow log n to the base k plus 1 plus 1. And this SAZN will get by that relation. The proof of this actually uses generalized arguments used for this proof. So we'll skip that and go to the next result. So in 2007, Shia proved that if n is a positive integer and p is a prime factor of n such that k is the maximum power of p that divides n, and if A is the set of all integers between 1 and n which are co-prime to P, then DAZN is equal to K plus 1. We generalized this theorem by showing that if n is a positive integer written as P1 power A1 up to Pm power Am, where these Pi's are distinct primes, and if S is an integer between 1 and m, and with respect to this S, if we take As as the set of all integers between 1 and n, which are co-prime to P1, P2 to PS, then with this weight set As, DAZN is equal to A1 plus A2 plus AS plus 1. To prove this, we use this fact that the unit weighted Davenport constant of Zn is omega n plus 1. So next, in the same paper, Shia proved another theorem that if A is an arithmetic progression of length ceiling n by 2 and common difference 1, Or in other words, A is a set of ceiling n by 2 consecutive integers. Then with this weight set, dAZn is equal to 2. We generalized this weight set also, and we took ceiling n by d consecutive integers. And the theorem is that if n and d are integers such that d is greater than 1 and less than or equal to n, and if A is a set of ceiling n by d consecutive integers, then dAZn is less than or equal to d, and SAZn is less than or equal to d plus n minus 1. Of course, here it is sufficient to show that dAZn is less than or equal to d. We'll see a brief sketch of its proof. Let S be a sequence of length d. We need to show that this S contains an A-weighted zero-sum subsequence. So we consider two cases. In the first case, we suppose that d divides n. So by the way we have taken the weight set A, we can see that it contains a multiple of n by d, and we'll call that multiple as u. And because the Davenport constant of Zd is d, there will be a non-empty zero-sum subsequence of this S in Zd. And now if we use this u as common weight, then that sequence, that subsequence along with this weight will give an A-weighted zero-sum subsequence, and we are through in this case. So in case 2, suppose d does not divide n, and if there is an element xi0 in the given sequence whose GCD with n is greater than d, then there will we will use this argument of case 1 and we will be through. So we can assume that every element of the sequence has GCD with n less than d, and with this assumption we can show that cardinality of this set xi dot a is cardinality of A, where this xi dot a is this set of all xi a coming from A. So let us assume, if possible, that this S does not have any non-empty A-weighted zero-sum, and write this sets xi dot A union 0 as BIs. Now we can apply Shirk's lemma to these D sets B1, B2, BD. This Shirk's lemma states that if B and C are subsets of an abelian group G of order n, such that 0 is in both B and C, and the only solution for this equation B plus C is equal to 0 is the trivial solution, then with these conditions, the set B plus C has cardinality greater than or equal to cardinality of B plus cardinality of C minus 1. This set B plus C is this sum set of all y plus z, y coming from B and z coming from C. So if we apply the Shirk's lemma to these sets B1, B2, BD, then we get that cardinality of set Bi, I running from 1 to D is greater than n plus 1. This is not possible because this set is a subset of Zn. So this contradiction shows that our assumption is wrong. There must be a non-empty weighted zero sum in the given sequence. So we are through in this case also. So yes, this completes the proof of that theorem. But as we saw in the statement, we could only say that dAZn is less than or equal to d. In general, we may not have equality. For example, if we take n as 13, d as 3, so that ceiling n by d is 5. And if we take this set A as the set of 5 consecutive integers, 4, 5, 6, 7, 8, then one can check that dAZ13 will be 2, which is less than the value of d. However, if we choose our weight set in such a way that 0 is not in any of these sum sets JA, where JA is A plus A taken J times, for any J between 1 and D minus 1. So we are choosing A in such a way that 0 is not here. Then the sequence containing D minus 1 ones will not have any A weighted zero sum sequence. And that will give us that dAZn is equal to D. So in the above example, this with same values of n and d, if we take A as this set, then we can check, we get that dAZ13 is 3, which is the value of d. And that happens because 0 is neither in A nor in set 2A here. So we get equality. It would be interesting to find some more conditions, look for some more conditions which ensure equality here. So we have one condition. So we move on to this higher rank groups. In particular, we will be seeing some finite p abelian groups of certain fixed ranks. So we first need Olson's theorem proved in 1969. It says that if G is a finite abelian group written as direct sum Zn1 up to Znr whose rank is 2, or if G is a finite p abelian group, then in either cases d of G is equal to 1 plus summation ni minus 1 I running from 1 to r. This summation will denote as d star G, so d of G will be equal to 1 plus d star G. So in the rest of this section, we will take P to be an odd prime G to be a group of this form, that is direct sum ZQ1 up to ZQD, where these QIs are powers of prime P and Q1 divides Q2 up to QD. And we will take this weight set A as set 1, 2. So with these assumptions, if we consider this sequence containing Q1 minus 1 by 2 times E1 and so on QD minus 1 by 2 times ED, where this set E1, E2 to ED is a basis for group G, then this sequence will not have any A-weighted zero-sum subsequence. Therefore, DAG with this weight set A will be greater than or equal to 1 plus length of the sequence, which is 1 plus D star G by 2. So if we consider a sequence of length D of G by 2, where D of G is the Davenport constant of G, and if T is S square, that is, it contains 2 times 2 copies of every element of S, then length of T is twice the length of S, so it has to be greater than or equal to Davenport constant of G. So there will be a non-empty zero-sum subsequence in this T. And now it is easy to see that a non-empty zero-sum subsequence here is an A-weighted zero-sum subsequence in S. Therefore, we can say that the AG is less than or equal to length of the sequence, which is ceiling D of G by 2. Since our group G is a finite P abelian group, we can apply Olson's theorem here and substitute the value of D of G, and we get DAG is less than or equal to D star G by 2 plus 1. We had the other side inequality in the previous slide, so we get DAG is equal to D star G by 2 plus 1, where the weight set A is set 1, 2, and G is of P abelian group of finite. Yes. So we have determined DAG. We'll now move on to determine SAG. For that, we will need some theorems and lemmas. The first theorem that we need is theorem by Adhikari, Grankiewicz, and Sun, proved in 2012. So if P is a prime and G is a group of this form, and we will denote the exponent of this group as Q. And if A is a weight set such that it does not contain any multiple of P, and any 2 distinct elements of A are incongruent modulo P, then if we consider any sequence of length P power M minus 1 plus ceiling D star G plus 1 by cardinality of A, then any sequence of this length will contain an A-weighted zero-sum whose length is a multiple of P power M. So in this theorem, if we substitute that rank of the group P is less than or equal to 4, that is D is less than or equal to 4, the weight set A is set 1, 2, and P power M is the exponent of the group itself, that is Q. With these substitutions, we can make these observations. So we'll see these observations as our next lemma. So here we will only look at this inequality that when the rank of the group is 2, SQA of G is less than or equal to Q plus D star G by 2. So this lemma, which we get by direct substitutions in the previous theorem, says that if S is a sequence over G whose rank is less than or equal to 4, and G is of course a P abelian group, and this denotes the length of the sequences. So if length of the sequences is greater than or equal to 2Q plus D star G by 2, then this S will contain an A-weighted zero-sum whose length is 2Q. Again, the sequence is greater than or equal to 3Q plus D star G by 2, and S already has an A-weighted zero-sum of length Q, then S will contain an A-weighted zero-sum of length 3Q also. So this part 1 of the lemma, we can write in terms of notations like this. When the rank is less than or equal to 4, S2QA of G is less than or equal to 2Q plus D star G by 2. We will call this as inequality 2. We will need this inequality later. So the next lemma. Let F be a field whose characteristic is not 2 and N be a positive integer. Then the monomials of the form product xi power ri, where I is running from 1 to n, and where ri, the powers ri's are at most 2, the monomials of this form constitute a basis for the function space from D to F, where D is this set, Cartesian product of n copies of 0, 1, 2, field F. So to prove this lemma, we define these monomials, these polynomials FUVWs over D like this. And we can check that this FUVWs take the value 1 exactly when this xi is 1 for all I in U, xi is 2 for all I in V, and xi is 0 for all I in W. And for any other n tuples, this FUVWs will be 0. So appropriately choosing these subsets UVW, we can span any function from this set D to F as an F linear combination of this FUVWs. And these FUVWs, from here we can see that they are in turn spanned by these monomials. So these monomials span the function space, and they are linearly independent also. So they constitute a basis for this function space. Yes. Now we are in a position to prove our main theorem. So the theorem says that if G is a group of this form whose rank is at most 4 and its exponent will denote as Q, then for any integer k greater than or equal to 2 and with weight set A as set 1, 2, we have as KQA of G is equal to KQ plus D star G by 2, where D star G is this summation. Moreover, when the rank is at most 2, that is D is less than or equal to 2, this equation will hold for integer k is equal to 1 also. So this theorem by Shia and Lee and independently proved by Adhikari, David and Urose also says that if the weight set A is this set 1, 2 up to R, then SAZN is equal to n minus 1 plus ceiling n by R. In this theorem, if we take n as the power of prime P, that is Q, and R as 2, then SAZQ will be Q plus Q minus 1 by 2, which is this equation 3 for K is equal to 1. Now, if we use induction on K, we'll get this equation 3 for cyclic groups. So we have got the theorem for rank 1 groups already. So let us now take that D is 2. If we recall, our observation 2 was that if when the rank is 2, SQA of G is less than or equal to Q plus D star G by 2. Now again, if we use induction here, we get SKQA of G is less than or equal to KQ plus D star G by 2. We have proved that this is an upper bound for SKQA of G. The other side inequality will prove later. Now we will take that rank is either 3 or 4. Let S be a sequence of length T, where T is 3Q plus D star G by 2. And assume if possible that this S does not have any A-weighted zero sum of length 3Q. Then our lemma, one of our lemmas, we can say that S does not have any weighted zero sum of length Q also. Now, let us define this polynomial P from set D to FQ, where this D is set 0, 1, 2 power T. We will define these P's as these polynomials. Yes. So, by using the fact that now there is no Q length or 3Q length A-weighted zero sum in the given sequence, and by using some properties of these binomial coefficients, one can get that the value of P is 0 when this T tuple alpha 1 alpha 2 alpha T is not 0, and it is 8 when this T tuple is 0. Now we use the lemma by Ellen, Nathanson and Ruza. It says that if A is a finite subset of field F and its cardinality is L, then for any integer m greater than or equal to L, there is a polynomial Gmx over field F whose degree is at most L minus 1 and whose value at alpha is alpha power m for all alpha in set A. So we use this lemma with set A as set 0, 1, 2. So what we do is we expand P as sum of monomials, and in any monomial that contains a factor xi power r, where r is greater than 2, we replace this xi power r by this polynomial grxi, whose degree is at most 2 and whose value at alpha is alpha power r for every alpha in the set 0, 1, 2. So we get a new polynomial, we'll call that as Q. And now it is easy to see that this Q is sum of monomials of this form, where this power of xi is at most 2 for any I. So Q is in fact now an FQ linear combination of the basis elements. And by the way we have got Q from P, it is easy to see that Q takes exactly same value as P at any element of set B. So Q also takes these values. Therefore, we can write by using the notation that we used earlier, we can write Q as 8 times this polynomial F, empty set, set of all integers from 1 to 2. U is empty, V is empty, and W is this set. And that turns out to be this polynomial by definition of FUVWs. So now we can see the degree of Q is 2 times T, which is 6Q plus D star G. But we can check that the degree of P is 6Q minus 2 plus D star G. This is not possible since Q is obtained by reduction of polynomial P. in a sense. So this is a contradiction. And this contradiction shows that our assumption was wrong. There is a 3q length A weighted zero sum subsequence in the given sequence. Therefore, S3q A of G is less than or equal to 3q plus D star G by 2. And our inequality 2 was S2QA of G is less than or equal to 2Q plus D star G by 2. So we can combine these two and we can say that SKQA of G is less than or equal to KQ plus D star G by 2 for any integer K greater than or equal to 2 when the rank is 3 or 4. And we had already proved this inequality for rank 2. So now we can try to prove the other side inequality. For that, for any integer K greater than or equal to 1, consider this sequence containing KQ minus 1 by 1 times 0, Q1 minus 1 by 2 times E1, and so on, QD minus 1 by 2 times ED. This sequence will not contain any A weighted zero sum of length KQ. So SKQA of G must be greater than or equal to 1 plus the length of this sequence, which is KQ plus D star G by 2. So we have the other side inequality also, and that completes the proof of this theorem. As we saw in the statement, we proved this theorem only for p abelian groups of rank at most 4. We expect this to hold for higher ranks also, but that we could not prove here, unfortunately. We are working on that, and hopefully we will be able to prove that also. Yes. Now we are in the last section, that is inverse problems. Here we characterize A-weighted zero-sum free sequences of certain lengths for some weight set A's, some weight set A. So first we consider this weight set 1, 2 up to R, and with this weight set DAZN will be ceiling n by R. So the extremal sequence for this will be like this. Any sequence of length ceiling n by R minus 1, that is 1 less than this, over Zn has no non-empty A-weighted zero-sum subsequence where A is the set 1, 2 up to R. If and only if it is of the form ceiling n by R minus 1 times U, where U is a unit of Zn. That is, every element is same and that element is a unit of Zn. We will skip the proof of this theorem and move to the next weight, that is set of all squares in Zn star. That set we will denote as Rn. And this theorem by Adhikari, David and Urose proved in 2008 says that if n is power of prime p, where p is greater than 3, or if n is a square free integer co-prime to 6, then with this weight set Rn, drn Zn is 2 omega n plus 1, where omega n is the number of prime factors of n, including multiplicity. Before characterizing A zero-sum free sequences, we will look at this definition that when this weight set A is a subgroup of Zn star, then these two sequences x1, x2, xk, y1, y2, yk are said to be equivalent with respect to A if there are elements a1, a2, ak in set A and unit C in Zn star, such that yi is equal to cai into x sigma I for some permutation sigma on k integers. So once these two sequences are equivalent with respect to A, it is one can check that this sequence has an A-weighted zero-sum subsequence if and only if this has one. So whenever we have A as a subgroup of Zn star, it is enough to characterize A zero-sum free sequences up to equivalence. Since here Rn is an example for such weight set, we'll characterize Rn zero-sum free sequences up to equivalence. So in the first theorem, we consider this first case that n is power of prime p, where p is greater than 3. Then any sequence of length 2 omega n has does not have any Rn weighted zero-sum subsequence, and only if it is equivalent with respect to Rn to the sequence 1 p up to p power k minus 1 minus v0 minus vnp minus vk minus 1 p power k minus 1, where these vi's are non-squares in Zn star. So we'll skip the proof of this theorem and go to the next one. Okay, here the other case, let n be a product of k distinct primes p1, p2, pk, such that pi's are greater than or equal to 7. Then any sequence of length 2k does not have Rn weighted zero-sum subsequence if and only if it is equivalent with respect to Rn to a sequence of this form, where this q1, q2, qk is a permutation of these primes p1, p2, pk. These ui's are squares with respect to qi plus 1, and these vi's are non-squares with respect to qi plus 1. So we'll skip the proof of this also. This is a list of papers that contains our new results. So I'll conclude my talk here. Thank you.
Thank you very much. Do we have